You have an assignment due on Wednesday. What questions do you have on it? Chapter 6, sections 1, 2, and 3. Yes, ma'am.
For question 16, where it's asked you to find the rectangle, how you do it?
It asks you to draw a typical rectangle and label it, right? So really, all you're asked to do is create that sort of a picture or that sort of a picture where you can label the height of that rectangle and its width. Well, in this case, that width is oriented across the x-axis, right? In this case, the quote unquote width is oriented along the y-axis. But if you know the boundaries, then you know each side. I kept drawing these as just little sticks. That's the same thing. Draw me what you consider the typical piece you're integrating so that we know what integral you're trying to set up. What happens often is people will, it's the easiest mistake to make is to not set up the height in the correct direction or to not set up the correct boundaries. So I just want to know, hey, you know what the boundaries are supposed to be so you can show it to me physically. Yes, keep it in terms of the variables. Use the boundaries that are the curves and the delta x or delta y for the width appropriately. The entire set, 6.1, 6.2, and 6.3 are visual to me. And I like drawing the pictures. I like trying to draw that 3D representation. I think that's helpful. If you think it is less helpful, then I want to know what I can do to help you either develop a sense of what is visual or develop the algebraic skills that you don't need the visual. But that's your call, not mine. More questions?
Are there general formulas for the rotations that might be a little easier to visualize?
Yes. In all disk and washer problems, it's a circle, so it's pi r squared. For a cylinder, it's circumference times height. So 2 pi r times our function. So I always think of these three formulas. And then it's a matter of tell me what your radius is. Whether you're rotating around a y-axis or an x-axis or some other line, tell me what your radius is for the disk. For the washer, you'll have 2 of them, an outer and an inner. Tell me which one's which. So I need to be able to at least draw the 2D picture, which I can graph on my calculator. And then I figure out where my outer radius is, where my inner radius is. For the cylinder, I'm almost always doing cylinders around a vertical line. So the height is going to be my function. And the radius, I need to know what vertical line I'm rotating around.
The way I remember it, it's kind of like function minus axis of rotation.
That's perfectly fine. No, it's almost always a distance. I don't think there's an easy formula that I can generalize into that sentence. But if you remember that the radius is your distance between your height mark and your axis of rotation, that's exactly.
Radius. What I'm talking about.
Yeah, when we're going this way. Right? Function minus axis of rotation. If I'm going this way, then it's x minus axis of rotation because that radius will be given by an x value. So does that statement help? When I'm going around a vertical line, I'm going to measure my radius by measuring my x value rather than measuring a y value.
Could you?
Absolutely. The pi can go out front, the 2 pi can go out front, no problem at all. They don't need to be inside. Multiplying by pi because I'm doing something with a circle, put the pi out front. In general, I believe that the setup of that little rectangle that we were just talking about in 6.1 does help us decide which direction my radius should be measured. Once I know what my radius is measured, I can do the rest of it. But remember, these formulas only apply for volumes of rotation, right? And when we're doing anything else, I'm thinking of my volume as integrating a cross-sectional area. And that could be done horizontally or vertically. So I think there's a problem where it says you're asked to integrate something and the cross-sectional area is a square. Okay, that's my area function, a of x. I need to figure out the area of that square depending on what x or y value I'm at. And when I set that up, I'll integrate it. When I'm doing a volume of revolution, that cross-sectional area function is one of those, a disk, a washer, or a cylinder. But if I'm just given a shape and told this is what the cross sections look like, then I need to create that using geometry. The example on page 454, examples 7, 8, and 9 are all about this. What one of them tells me I'm integrating a circle, but all of my cross sections are equilateral triangles. There's the solid object right here, like we made it on a 3D printer. But if I slice that this way along the x-axis, you can see those triangles built up here. So if I were to build it instead of bottom to top, if I were to build it back to front, I'd be making a triangle each time and layering it in. Now I find the area of that triangle, and that's the thing I integrate from one side to the other.
It's a real good 3D picture of that shape. Tell what you like with the process.
I need to be told something about that shape, right? I need to be told what its cross-sectional pieces are, or I need to be told the way I build it.
So you can we'll rotate this way out. Yeah.
Yes, if I'm told rotate, then I'm going around an axis, right? My cross-section is some sort of round object.
So
That's either a disc, a washer, or a cylinder. It's not a round object. I need to figure out how to build it. I need to be told what it looks like. Like this one. This is a lovely discussion. I'm going to build a pyramid. Welcome to Egypt. I'm going to build the pyramid by stacking a bunch of squares. Okay. I'm stacking a bunch of squares. I need to know what the area of the square is based on how high it is. I need to know the angle of the pyramid at the side. And then I use a bunch of geometry to figure out how big that square is. But yes, I have to be told something about the way in which my solid is built. I think I have that video. If you are planning to take the 3D printing art course, one of the things you will learn is that if you take a picture of a solid object and scan it in carefully, you can then use a computer program to slice it up. And that slicer image tells you what you're going to lay down at every step. Then we go in and we say, oh, are there empty overhangs? We need to build support pieces. And that's what a lot of these solid print object things like the maker files create, is they create the appropriate STL file to support all the pieces by doing that math behind the scene. But when I'm trying to program math objects to build them this way, I have to give it all the formulas up front. More questions? Yes, ma'am. I'm sorry, I can't quite hear you. 24. So 24 says, here's a thing, we're going to rotate it around a given line. All right, do you want to look at number 23 or number 25? Your trigonal are right. So I'm going to integrate from 0 to pi over 4. And then I need this. I've been given two equations, cosine and sine, right? And when I draw those between 0 and pi over 4, cosine starts at 1, sine starts at 0, and then they cross. So I have this little curvy flag thing. There's my picture. That's the thing I'm rotating. What are we rotating around? About y equals. So that's down here. I've got an outside radius, I've got an inside radius. Outside radius, inside radius. Closer to the rotation axis, further away from the rotation axis. I'm going to spin this, so I'm going to get a washer. Here's that little rectangle that Chloe was asking me about earlier. I think of the outside radius as going from here to here. And the inside radius going from here to here. They both go to the axis of rotation, right? But they start at different curves on the top.
What should the X rotation be center of that? Say, should that out radius be the same distance away from the bottom as the top?
Yes, but I measure the radius from the center to one edge, not to the other edge. I only have to, I'm not measuring a diameter. I have not done the spin part of this. I've only drawn it on the flat part. Because remember, this slice is going to go this way, right? It's going to come out and back. Again, I'm visualizing a washer held sideways here. Once you come up with these two equations, R out, R in, because I put the pi out front, I got to square them. Then there's a whole bunch of trig I have to do. You should be grabbing the trig functions handout on our Canvas page. But the most commonly used trig functions I'm going to need are things involving the cosine of 2x, the sine of 2x, and Pythagoras. Almost all the rest of it is going to be less useful. Better? Okay. This is what I meant by algebraic. I need the axis minus the axis, right? So I can figure out what those are, and then I can put them in. More questions? Yes, ma'am.
Are there gonna be more problems like this?
I haven't counted what's from what, but I think it's about 25% from each. 25 from exam 1, 2, 3, and the new material. I think so. That's why I put the review sheet up. That's got everything. I didn't count. I can, I just haven't yet. It's okay. Okay. More questions? Yes, ma'am.
Question like through sort of I set everything up,
Uh-huh.
but then I would, I didn't know what to do because it would just be over.
Fortunately for me, it says in part B, use a calculator or a computer to evaluate this. You don't have to do this by hand. I just need to know what the angle, the integral is. So once you've written out the integral in part A, I then am going to go into the math button, and way down there on option number 9, it says function integrate. And once I hit that, I can type in the integral. If you see the word FNINT and a parenthesis here, you have an older version of the software, come talk to me. I know the syntax for that. There's a way to do it there too. It's just a little messier. It doesn't look right. But if you see this, just type in the integral, exactly the integral you wrote out in part A, verbatim. So if I'm going to integrate from, I don't know, 0 to pi over 4, whoop, not pi times 4, pi over 4, pi times stuff, I can just type it all in. And at the very end, I'm integrating in x, so I'll put a dx there, hit enter, it'll give me the answer. How did I get, so under the math button, keep it going down until you see option number 9. That little arrow tells me there's more stuff down there, and there it is. The calculator does so much stuff. It's a computer program. I'm showing my age again. I found, helping one of my friends clear out a house they're moving out of, I found my first computer. I wish I was making this up. That's a programmable computer. Because what it has is a magnetic tape drive. You can actually put programs on this that come on little pieces of magnetic tape. Matrix multiplication, complex variable arithmetic. People, this is from 1965. This was before I was born, but my father had one. And I learned how to use it as my very first computer. And I found one in Robin's house and he gave it to me. This is a computer. It just happens to fit inside a calculator body. So does this one.
It does actually give us like questions. It just want us to solve this and give it cross sections.
Yes, it wants you to tell me the volume of an object with that cross section. So that's the one we're going to have to build the cross section. But right, but we're going to have to build the equation for it. My recommendation, you should know as many of them as you can, but the ones I think are absolutely essential. By the way, these two come from taking this and putting it in here. So really, those two are optional. You can rebuild them from the other ones. Everything else that's in that giant pile of trig functions is nice, but these are the ones I use the most. I know that there are a large number of other trig formulas and relationships that show up depending on your field of study. I know that the forensic science people do a lot of inverse sine stuff. So there's some nice approximations for the inverse sine because they're doing angles of impact for blood splatter. I remember that in the forensic analysis course. It's what happens when my office is next to Dr. Flowers. I find out all this stuff. There's a lot of linear approximation for drop, for bullet drop, but we're using the linear approximation we came up with. So we've seen all these formulas. Again, what you use depends on what field you go into. I know people who have huge numbers of vector analysis pieces for their structural engineering, mechanical engineering pieces, and they use a lot of matrix algebra. So they have all of those formulas memorized. I look them up.
Number 54, would you actually say on volume by any method? What is it referring to by any method?
Well, you could use a volume of rotation using a disc, a cylinder, a washer. What's the most appropriate for that problem? You tell me.
So it's not like multiple applicants?
Yeah. Some of them are undoubtedly going to be easier than others, but I'm sure I can do it in multiple ways. I think that problem can be done both with discs and with horizontally oriented cylinders, but we didn't do horizontally oriented cylinders because they're hard. So I would probably do it with discs.
Did you do?
Do you want to look at 53, 55? Pick one. 55. Which says, take the region y squared minus x squared equals 1 and y equals 2 and rotate around the x-axis. Well, that's disgusting. However, I look at that and I go, wait a minute, y squared minus x squared equals 1. I've seen that equation before. I've seen that equation before. That's a conic section. So I go back to my conic sections handout. Remember, where there's a minus in the middle, that's a hyperbola. When the y is positive, it's going up and down. When the x, okay, I know what this looks like. Which means I can start with a crappy picture. That's my hyperbola. And then I have the line y equals 2. That's going to be here. So really, this is the thing I'm going to rotate. That little piece of hyperbola cut off by that horizontal line. That means it's going to have a mirror image down here. And we're going to go around the x-axis. Yes? Yes. Because I know this is positive, I'm going to want to look at where this is positive. So I'll take that equation. And I'll look at the positive part of it. Absolutely. Yep. And then y equals 2. Except I made a typo. Somebody catch what typo I made. Yeah, if I move the x squared to the other side, it becomes positive. Makes a big difference. There's my hyperbola upper part. And there's my, there you go. Perfect. Wait a second. I'm rotating this way, right? Around the x-axis. So this piece is going to end up folded down here. And that means there's going to be a space in the middle. I need a washer. Because as I cut this way, I have an inner circle, and I have an outer circle. So I have a washer here. Aha! So the outer radius hits which curve? And that's the same all the way around, isn't it? No matter what x I'm at, that radius is 2. What about the inner radius? Now, I need to know where these cross in order for me to figure out what the limits of my integral are. So I take this equation and I set it equal to 2. So I'll get plus and minus the square root of 3. And now I can set up my integral. Outer radius squared minus inner radius squared with a pi on each one. I'm really happy about having the square root now because it goes away. And if I factor out the pi, that turns into really an easy integral to do. As a matter of fact, I can even make it easier. How can I make that easier than that? Actually, the picture helps. Let me leave the picture. There's a really nice exploit that I can use here to make this integral easier to do. Ah, yes, thank you. Without that root 3, I can't use the exploit, so thank you for catching that. It's symmetric. I'm going from minus number to number, aren't I? And look at this function. X to the 0 power, X to the 2 power, those are both even powers. And the picture is the same on the left as it is on the right. This is an even function. 2 from 0 to root 3. And then one of my numbers that I'm plugging in is 0. And that made my life so much easier. Now, if you didn't notice that, that would be okay. You'd get the same answer whether you do it this way or this way. But now I'm plugging in a 0, and plugging in 0 is always easy. See what I mean about liking to plug in 0? Plugging in 0 gives me 0. And I don't have to worry about taking the negative square root of 3 to a bunch of powers, which is always nice. Square root of 3 cubed. Yes, but I don't think that helps me. I can write it as 3 to the 3 over 2 because the square root's a 1/2 power. But I can think of it as doing the square root of 3 times the square root of 3 times the square root of 3. When I multiply two of them, I get 3, don't I? But I'm dividing by 3 as well. 3 root 3 over 3 just becomes root 3. So I get 3 root 3 minus just root 3 times 2 pi. Wait a minute. 3 thing minus 1 thing is 2 things. And there's an exact answer. If you had done this with the negative square root of 3, you'd get this same answer. You just have a bunch of other minus signs to worry about in this part of the calculation back here. Instead of zeros, you'd have these with negatives in them. It would still work. You'd only have a 1 pi out front. So in any even function, I believe this is in chapter 5, section 5 at the very end. The integral from minus a to a of f of x dx is 0 if f of x is an odd function, or equals 2 integral from 0 to a f of x dx if f of x is an even function. And our definition of being odd is that f of minus x is minus f of x. So what's up on the right is down on the left, and what's down on the right is up on the left, that diagonal symmetry. And an even function, f of minus x is equal to f of x. The left side is an exact mirror image of the right side. And because I noticed that both in the picture as being a mirror image and in the integral as well, the actual function, that's why I was able to do it. Page 424. But notice that I had to set up the integral completely first to see that I could do that. I can't just assume, oh, I've got functions that have nice behaviors. My integral is going to give me that. I have to look at the actual thing I'm integrating and verify one of these properties. 3 minus x squared. I know what that graph looks like. And it's the same on the left as it is on the right. Yes, ma'am. Okay. Uh-huh. So your integral involves this square root of x minus 1, and it involves the y equals x minus 1. I think it's like that. I'm not sure if that's the right order, but let's run with it. I think you're integrating from 1 to 2 in this problem. So there are two ways to do this. If you make the u substitution like this, then yes, you do it to both parts. But you could also split it into two integrals. And then you can do the u substitution here and not do it here, because now they're separate integrals. And I can do the first one completely separate from the second one. Now I got lucky that both of those look like x minus 1, so it makes my substitution easy. But yeah, you can do it as one fell swoop across that hop integral and substitute in both places. You don't have to, but you can. There are a lot of places where splitting an integral like this is helpful. And there are places where you look at this and go, it's going to suck either way. Let's just leave it together. Better? More questions?
Can you check your answer? To integrate terms of y and x?
Oh, if I'm doing the integral here, I can give it the letter y. Instead of hitting the x button, I can hit the alpha, and then above the number 1 is the letter y. I can give it the problem all in y. Or I can change the letter in the problem and write in the same integral just using x's. Give me an integral in y. Well, let's look at 3. 6.1 number 3 has x equals e to the y. It has a parabola, x equals y squared minus 2. And then it goes from -1 to 1. Right? So if I set up this integral, it's going to be the integral from -1 to 1. Chloe, here's where I do the draw the little rectangle piece. Okay, my little rectangle is going to look like this. Its thickness is going to be a dy, and its height goes from the x on the right to the x on the left. So its height is e to the y minus y squared minus 2. But Emily, the important part is that the letter in this integral doesn't matter at all. I don't care what letter you're using there. So you could just as easily write in your calculator the integral from -1 to 1, e to the x minus x squared minus 2 dx, and you would get exactly the same answer.
How would you have all the numbers assigned correctly?
Once you know what you're integrating, the letter you choose to integrate with is a dummy. You can use any letter you want. The integral from -1 to 1, e to the smiley face minus smiley face squared minus 2d smiley face. Same thing. I don't care what the letter is. As long as I know that this is a number, that works. I don't know what you use the domain of smiley face for, but somebody created a file that allows me to use emoji in my typesetting files, which means I can do e to the Among Us characters. Why not? Whatever symbol you want. I did an entire problem in suits of cards. E to the heart, D heart. I might have told you the story, I might not have. My undergraduate year, I decided I wanted to take part in the Putnam competition. The Putnam competition is a math exam. It is a 6-hour math exam. 3 hours in the morning, 3 hours in the afternoon. 6 problems in each set. 10 points apiece. I scored a 6. But we had an entire semester of training for the team that the University of Florida was going to put forward. And there were like 12 of us in the room working on this stuff. And my instructor for the Putnam seminar was a Russian mathematician whose first name is Boris and whose last name I've completely forgotten. But Boris would actually write integrals in crazy variables just to mess with us. Stick figure, that's where I got the stick figure from. But Boris also had this lovely issue of being Russian, and he'd waited in one too many bread lines, so he used loaf of bread every now and then. It doesn't matter. The variable itself is a convention. Do you know why we use the letter X? There are two different stories as to why we use the letter X, neither of which are verifiable. Algebra was invented in Persia. It is Arabic, al-yabar, the method. Algebra is preventing us from doing geometry. Y'all loved high school geometry, right? I think I'd rather hit myself in the head with a brick. Algebra was invented to stop doing that. When Pierre Fermat and other people reading the algebra translated first from Arabic to Latin and Greek, they were asked about this thing that they were always working with. As a matter of fact, in Arabic, the word is shy. I am absolutely going to maul this. But the symbol for shy looks kind of like that. Some diacritical marks. I think the dash is under, it might be above, I'm not sure. But it's the thing, and it was translated into Latin as the thing. But most of these mathematicians were Italian, so they translated the thing into Italian. Anybody speak Italian? What's the thing? What's the in Italian? The is c'è. C'è cosa. But you're writing in the Latin alphabet. C'è cosa. C'è. Chi. It's an X. It's a great story. I have no idea if it's true or not. The thing we're doing, we're looking for an X. They stopped writing out the rest of the word and just stopped writing that. One letter, who cares? Use loaf of bread. I'm going to my office hours next. If you have questions, you should come see me there today or tomorrow. This assignment is due on Wednesday. I will see you all then. Have a wonderful day.